Hello, my name is Alastair Basden from Durham University, and I'm going to be talking to you a little bit about what we're doing with our NVIDIA BlueField system here at the university. There are a number of others that have been involved with this work. We're, as well as being part of Durham University, we're also part of DINE and Excalibur, and I will explain what those are later on in the talk. Let me first start by telling you about our Cosmo HPC system. So Cosmo is the cosmology machine. It's a HPC system dedicated for simulation of cosmology, effectively. It's part of the UK DIRAC Tier 1 national facility. It started life in 2001 as Cosmo 1, and it's now in its 8th generation, Cosmo 8. Cosmo 8 is a Dell system based on C6525 servers, has 128 cores per node with the AMD 7H12 chip, 46,000 cores. We have a terabyte of RAM per node and a full HDR200 non-blocking fabric with a factory topology. We also have direct liquid cooling on chip, 5 petabyte bulk storage system attached to it, and a 1.2 petabyte fast scratch storage system for dumping our restart files onto. And this runs at about 400 gigabytes per second, not gigabits, gigabytes per second. So it's really is something fairly fast. Durham University is a Dell Centre of Excellence, and here we focus on smartNICs. This is very relevant for this talk. smartNICs and HPC for communication protocol offload, evaluation of high-speed, low-latency technologies, and implementation of reconfigurable or composable architectures for HPC infrastructure. Now, let me move on to DINE, which is our Bluefield system. It's a 16-node test cluster for novel technologies. It's based on, again, Dell C6525 series servers, dual 16-core AMD Rome per node, 512 gigabytes per node, and in these, at the moment we have our Mellanox Bluefield I cards installed. These provide 16 cores of ARM per card, per node, and 25 gigabit Ethernet. So this is just an image of DINE, not particularly interesting, but it just shows the, it's the half width 1U servers. So what is NVIDIA BlueField? So Bluefield is a programmable network adapter card. As the Bluefield 1 cards that we have, they have 16 ARM cores on them within the card itself. A dedicated network interfaces, 16 gigabytes of RAM on the card, and a dedicated ConnectX-5 chip. So to the server, it can look just like a standard ConnectX-5 card. These cards, Bluefield cards, have two operation modes: embedded mode, where they act just as an embedded switch, and then you can do virtual switch offload, or as a separated host mode. And this is the mode that we tend to run them in, where the card and the host have independent MAC addresses, and therefore the host and the card can send and receive RDMA packets, RoCE packets, etc. between themselves, and of course to other nodes. So one host can send packets to a Bluefield card in another node. So you've got all sorts of things that we can do there. Now, why are we interested in Bluefield? Well, firstly, it brings lots of flexibility. And one of the problems that we wanted to try and solve with this is the MPI progression issue. And I'll explain what that is in a minute. But basically, it's that messages do not get progressed. And this causes delays in both the sender and the receiver. Now, this is we're going to use the programmable Bluefield cards as stepping stones here. So messages are first sent to the Bluefield card. The sender, the host, can then continue with doing its processing. The Bluefield card then passes the message on to the relevant receiving card. These messages are then RDMA'd into the host, that's receiving those. So effectively, the messages are forwarded and buffered by the Bluefield cards, and this is seen to improve performance for when using many small unexpected messages. So we're going to talk here about MPI progression. What do I mean by MPI progression? Okay, let's say we've got two nodes, node A and node B. Okay, and node A is sending its data to node B. So at TA0, we call MPI send, so asynchronous send. At some point later, at TA1, the data is actually left. Some point after that, we want to check, has the data left? So we call MPI test to check this, and MPI at TA3, MPI test returns, confirming the data has gone. Now on node B, at some point we call MPI iReceive. Okay, some point after this, TB1, the data actually arrives. We then call, so this was an asynchronous receive. We then call TB2, we call MPI test to check whether the data has arrived. This function then returns to confirm that the data is here. Now, TA1 and B1 are not measurable, so we can't actually measure when the data is left and arrived. Depends on many things, but we do know that TB1 has to be greater than A1. The data cannot arrive before it's left the machine it's coming from. What we want to try and do is minimize the time between finally receiving the data here and when we actually started, when we first called to send the data, and also the time between confirming the data has gone so that we can get on with reusing that memory and when we actually send that data. Those are the two things that we want to minimize. Only part of this is network bandwidth limited. The latency is also important. So according to the MPI standard, A3 minus A2, let me just remove my head for a minute, A3 minus A2, and so this is the time from calling MPI test to MPI test returning, assuming the data has already left. That should be 0 or measurable. Likewise, if you assume the data has already arrived, then the time between calling MPI test and it returning again should be 0, measurable. It should not do any work. But what we find is, and this is a fairly well-known phenomenon, in rare cases, TA3 minus TA2 can be very large. You can be talking hundreds of milliseconds for this. And basically what you're doing there is you're handing off control to the MPI library, and presumably it then does some sort of internal housekeeping. So what we're looking at trying to do with the Bluefield is solving this progression problem by moving MPI work to the time between time B1, which is the data arriving, and time A1, data leaving. Now if we try and do that, that doesn't help. Okay, because that actually doesn't solve the problem. Now, if you have an RDMA implementation of all this, you may not need to call MPI test, but you do still need to check. You do still need some sort of MPI call to check that the data is there. MPI probe, for example, so that the library has time to regress itself and move the data. Background flags also, we find, do not help. And this plot just shows the time of the start of a send against the time of data arriving. Okay, for different message sizes coded by colour. Larger messages obviously take longer. And ideally, what you would see is a straight line here. And you can see that generally speaking, there is a bit of quite what happens here. Well, you can ignore that, pretend that's straight. There's a very generally small messages, but just straight line. Now, but what we do see is that these spikes off the line. These are the MPI progression issues. This is where it's taking an unexpected length of time. Can be a large amount of time here. Unexpected length of time for you're talking over a millisecond there, over 1,000 milliseconds there. Unexpected length of time for this message to actually be sent. So some of the work that we've been researching as part of the Exahype development, which is a UK funded project. Funding has come from Excalibur, which is the UK Preparation for Exascale fund, and from the Exaclaw project as well. Also, we have some EU funding for this from Cheese. So, the first idea that we look at is, which was published at CCPE last year, is that we take tasks that are to be processed and we move them temporarily to another node, to another rank, which is less busy. So let's say you've got loads of nodes that are all doing their processing, and they're busy doing this processing. Now, in an Exascale system, you want to try and balance that processing as much as you can. So if you've got a task that is waiting to be processed, but it's on a node that's currently busy, what you can look at doing is moving that task and the data associated with it perhaps to another node that's currently not busy. Maybe it's waiting for MPI data. So what we're doing there is we're using the MPI wait times for something meaningful. The key challenge here is you've got to get the message quickly from the busy rank, the slow node, to the one that's fast, to the one that's not doing anything, that's just waiting. Process it quickly and return it quickly. So you need low latency there on what is probably already a congested network. This local challenge is mastered by, so we master that locally by tweaking the task system and giving migrated tasks high priority. So we do have this remaining challenge, which is the MPI progression. And we want to see it. We also want to try and reduce the impact on the main communications. The second idea, which again was presented last year, this time at ISC, is replication of MPI ranks. So you have multiple ranks, multiple nodes, are given the job of computing the same task. Okay. Then you allow the tasks to share their results with the replica ranks, with the ranks that are doing that same identical processing. Okay, and that means that then the node that has produced its data first, it's done this task first, is then shares its results with the other nodes. Most of those won't yet have started doing that task, so they don't need to run the task, they've got the result already. There might be some that are already run the task, in which case they can either be cancelled or just left to run, whichever is easiest for programming, I guess, whichever is most efficient. The key challenge here, of course, is getting the outcomes of the completed task quickly to the other ranks, so that if you have a long delay there, of course, then they all end up computing the same thing. So again, we can do this locally by mastering the task, by tweaking the task system. We managed to do that. But again, the remaining challenge is this MPI progression issue and data transfer orchestration of the speculatively needed outcomes. So how you share the data between all these different nodes that are doing the same task. And this is where DINE, our Bluefield system, comes in. So what we aim to do is move tasks to other ranks. It's all about moving tasks about a large HPC system. And what we're going to do is we allow the Bluefield cards to orchestrate the task movement. Which task should move to which other rank? How the task is injected into the rank local tasking system. And what we're going to do is we're going to let the Bluefield cards basically serve as a cache. So the task results, which are transferred speculatively, are held on the Bluefield card. So you've got a node that's produced its results, it's transferred those results to the other nodes, well, to the Bluefield cards on those other nodes, which might want those results. Those results then don't get transferred to the node itself, they stay on the card, and the target rank that was also going to process that task can, instead of processing the task, it can grab the result from its local Bluefield. Doesn't have to go to Fabric this time, but its local Bluefield because it's already there. If and only if the data is actually needed by that rank. So some lessons and best practices that we've learned from our Bluefield system. The ping pong benchmarks, the OSU benchmarks, actually give poor performance. This is because if you're ping ponging between two hosts over a Bluefield card, you've got to ping, the message has to go into the Bluefield, and then to the next across the fabric into the receiving Bluefield, and then to the host. And to improve that, what we need to see is development at the level below MPI, so at the UCX layer. And we're awaiting some resources to start some investigations into this. We also need HPC code modifications to get the most out of Bluefield. And again, extensions or modifications to MPI may be necessary. And what we found is that running in host separated mode has been most useful. We've got the ability to run separate MPI processes on the ARM processors. Single MPI call, this is important, the single MPI call is then called to launch processes on both the x86 hosts and the ARM cards. So that has been also very useful. Our future plans, the Bluefield cards need to be able to drive non-blocking communications. So this should become available as Bluefield II. It's, I believe, currently being implemented, and this will become an upgrade to our DINE cluster. We aim to upgrade it with another 16 nodes, fill them all with HDR 200 Bluefield 2 cards. These have 8 ARM cores, not 16, but 8 cores, but at a much higher clock rate, so more than twice as fast. So that's actually more appropriate for the sort of stuff that we want to do. We also want to investigate the RDMA capabilities, direct memory access to remote nodes, things like that, and augment the Bluefield processes with application knowledge. So start looking at some of the data semantics. Finally, it's important to consider the road to exascale. How do we get from where we are now to exascale computing? Data transfer with an exascale system is going to be a bottleneck. The use of smartNICs can reduce the data transferred and also, most importantly, optimize the data flow. Runtimes can be reduced by ensuring task mobility, moving tasks to the data, but also moving tasks to nodes which aren't as busy.
Hi, Alastair. I'm John Lockman with the Dell HPC AI and Innovation Lab, and that was a really great presentation on the Bluefield II SmartNICs. Can you tell me a little bit more about how you're using the SmartNICs at Durham?
Yeah, so we've got a cluster, a small cluster, kind of a test cluster, which we call DINE, D-I-N-E, in which we host our SmartNICs. Now it's a 16 node cluster, and what we do is we use it to experiment with different ideas that researchers have in how they can get the most out of these SmartNICs. Now, a lot of what we're trying to do at the moment is all to do with tasks, MPI tasks, moving tasks around. So you can imagine a large cosmology simulation or something like that. Any sort of simulation, it's there, it's running on multiple nodes and it's doing its tasks. And you might get to the point where the simulation becomes unbalanced. You know, as you evolve a universe, for example, you tend to get bits of the universe become more and more dense, and other bits become there's almost nothing there. So you might get to the bit where stage where different nodes have more work to do than others. Now, what we can do with these, what we're hoping to do with these SmartNICs is to be able to look and see, okay, this node is extra busy. Let's move some of the tasks that this node is doing onto some of the other nodes, compute them there, and then very quickly send the results back via the SmartNICs to the node where they should have run, and then MPI just continues as if it had been done locally. So that way we're moving tasks around, using the SmartNICs to do load balances. So that's one of the key things that we're kind of interested in. Another idea that we've had that we're trying out with them is what we call speculative execution, where we know that we've got a task that needs to be computed, but we don't know which node is going to be available first to do that task. So what we do is we say, well, what if we assign that task to multiple nodes? Then the first one that computes the results for that task then shares those results with the other nodes that might also have computed it. And therefore the nodes that are about to compute it, they can look and they can ask their SmartNIC, has this result arrived yet? Because the result, when it gets computed, it only gets sent to the SmartNICs, doesn't get actually sent to the host. So then they only have to ask the SmartNIC, doesn't have to go over the network. Ask the SmartNIC within the server, have you got a result yet? If they have, they just use that result. If they haven't, then they know that they're the first one to start computing. They compute their task. Now, of course, doing that, you might get the situation where two nodes are computing the task at once. But you know, it's a small loss for what we hope will be a fairly decent gain in simulation speeds.
Can you touch on some of the specific algorithms that you see that are being accelerated because of this model?
A lot of them are fairly unique for the physics involved in the system. So, you know, it might be, for example, simulations of dark matter and how that interacts, fluid, large hydrodynamics calculations, things like that. So it's all to do with a lot of it's to do with the universe and different bits. And of course, in our models, if we're simulating different things, we can turn on and off bits of physics. So we might have a simulation that is only gravity. Then we might have one that is gravity and dark matter and dark energy, and you know, combine all the physics we can. And they all run at different speeds, have different balancing issues, and so on.
The load balancing sounds like a really complex algorithm that you put forward. And it kind of sounds like you're looking a little bit more towards sort of a PGAS model, or even a active message type of a model for programming this. Now, your primary work has been in accelerating MPI workloads, but do you see the SmartNIC sort of accelerating other distributed programming models like shared memory, PGAS, or other things like that?
Yeah, certainly. So one of the things that we are looking at is a direct RDMA type approach, where we kind of, so to get rid of the MPI progression issues that we've been seeing, where tasks can sometimes hang for a long time just waiting for MPI to do stuff in the background. To get rid of that, we're looking at going at a deeper level and doing MPI. And there, we can MPI from the host to the card. We can MPI from the host to another host, RDMA from a host to another host, or we can RDMA from a host to a card that's attached to another host. It gives all sorts of flexibility for moving our data around, putting it where we want it, without actually disturbing the nodes where processing is going on if they don't want that data. So
always key to be keeping that RDMA movements away from the CPU, right? And let it just keep doing the flops and computing your problem.
And so we can end up using these SmartNICs as kind of like a cache, if you like, in a way. They cache the data, and then if the CPU that's attached to them needs it, it just requests them, and rather than having to go over the network to get what it wants, it's there kind of locally ready for it.
So kind of pre-caching, sort of tiering memory for you. Is that what you're kind of describing then?
Yeah, I guess it's a bit like that. Yeah, or caching, pre-tiering memory perhaps, or caching results. Yeah.
So with technology like Bluefield, we're adding compute in the network now, right? How do you see that's going to drive change in future releases of the MPI standard?
I think there's going to be a lot more flexibility needed, because where you've got compute moving into the network, you want to allow different types of compute to be done in network. From different vendors may have different ideas of different computes they want to do in the network, and you need to have the MPI libraries flexible enough to be able to cope with that. And particularly as you want to move towards larger and larger systems, that can become more and more important.
So you guys have had, your team has had roughly a year or so working with the Bluefields now, is that right?
Yeah, probably a bit less actually. So you get maybe 9 months, something like that.
Maybe 9 months. Okay. Do you have any best practices or guidance that you would give to others who are just now getting started?
So the first thing I'll say is it's not trivial. It's not simple. One of the things the Bluefield cards themselves can be run in two different modes. One is what they call an embedded mode, where it kind of acts like an embedded switch. The other is host separated mode, where both the host and the Bluefield card have their own MAC addresses. They can then address each other, but they can also be addressed. And that's the mode that we're using, that we found most useful, because it gives you most flexibility, gives you most power to do exactly what you want to do. Now, of course, what we do with our codes is we compile two versions of the code. We compile the x86 version that runs on a host, and then an ARM version that runs on the Bluefield, and then we do an MPI run that will launch all of those at once in the right places, according to where it's going. So that's a useful thing to have ready. Simplifies things a lot rather than having to try and use. So it's good. We find it very useful to use, even if we're not using our MPI for communications underneath. It's a good way of launching these tasks at the same time in the right places, etc.
So you're kind of grouping your MPI tasks then. You have like Bluefield MPI tasks and on-host MPI tasks. Is that how that works?
That's right. Yeah. So basically, what we're looking at doing is the on-host ones are doing the science calculations. The Bluefield tasks are then the ones that are responsible for moving data, for moving tasks around if that's appropriate, and things like that. Now, of course, all of this is in fairly early stages, so we haven't got something yet that we'd want to put into production code, but it's all ideas that are formulating, stuff we're trying, things that we're gradually working out. Now, one of the things that we do find is that because you've got, if you want to go from host to Bluefield to host, you've got quite a lot of steps there, more steps than if you're going directly from host to host. And so we one thing that we do find is that can add a fair bit of latency, perhaps even more than you might expect when you use MPI. And so we suspect there's work that needs to be done below the MPI level, maybe at the UCX layer or something like that, to try and bring that latency down, to try and understand a bit more about the type of fabrics, the devices and hosts that we've got attached and that sort of thing.
And in your setup, are you using primarily InfiniBand protocol, or have you taken a look at the Ethernet as well?
Our Bluefields are all Ethernet.
It's all Ethernet.
Yeah. So we've got the versions with the Bluefield 1 cards we've got at the moment are 25 gig Ethernet. We are looking, when they go GA, we're looking at getting some HDR 200 Bluefield 2 cards. So that will be kind of our next step.
What would you want in the next generation of SmartNICs that you don't have today?
I think something that we would want actually is perhaps something more like Gen Z, where the device is attached to the memory bus and not the IO bus, because that then makes it much easier to do what we want with moving tasks around. Because if you've got a server, some servers that are there talking to a bank of memory through their SmartNICs, then, and if they're going through the memory bus, then you've got much better access to that kind of remote memory. You can make your memory remote and then move your tasks around to the place that's best suited to compute it.
Are you working with any other research teams outside of Durham?
Yeah, so we're part of the UK Excalibur program. So Excalibur is the UK's preparation for exascale fund, and as part of that, mostly it's a software effort, but it has provided about 10% of the budget is for hardware, for novel hardware that might be coming along the line for future exascale systems. And so we're working with some of, so we are actually, some of the hardware that we host, our Bluefield II system will be one of these. Some of this hardware will be funded by Excalibur, and therefore is made available to the Excalibur research groups throughout the country. So, other groups will be accessing the Bluefield system and looking at that. And we've already started some of that process. And so there are other groups that use our Bluefield 1 system.
It sounds like this kind of technology might be integral to the development of exascale systems. How do you feel about different technologies that you're looking at when you're thinking about exascale? What do you find to be the most important elements to look at hardware-wise? If
you've got a lot of cores or a lot of compute, whatever that would be, you looking at the network is a very important thing to do, I think, because you've either got to transfer your data around the system, where you need huge bandwidth, that sort of thing at these scales, or you've got to be transferring your tasks, in which case you want low latency and you want some fairly high bandwidth again to do that, plus bandwidth for the task to be able to access this memory wherever the memory is, if it's a central bank of memory or something like that. So I think it's a lot of the key will be based around the networking, but also minimizing the amount of data that's transferred. Now, whether that's done in things like smartNICs or in smart switches, or and of course smarter algorithms, that's I think you need all of those things in the mix.
Well, it sounds like you guys are having a lot of fun with these smartNICs. I look forward to the papers and talks that you'll have in the future about these, and we'll be looking out for more information from Durham on the Bluefield smartNICs.
Yeah, sounds good. Yeah, hopefully we'll have information out there.
All right. Thanks, Alastair.